Hi, I'm Dan from LearnCube. Thank you for joining me today. I'll show you the new feature in version 3 of the Kubernetes instance calculator, including the new cost sensitivity widget. Let's dive in. First, a quick refresher. The Kubernetes instance calculator helps you find the most cost-effective node size for your workload. Let me show you with an example, a Node.js app needing 4 GB of memory and 1 CPU. Now let's sort the results by cost per pod. The calculator instantly shows that a T3A 2x large at $1.03 per pod is your best bet. But here's what makes this tool special. It accounts for the hidden costs of Kubernetes, reserved resources for the kubelet, operating system, and eviction threshold. You can compare instances side by side to see efficiency metrics, overcommitment risks, and maximum pod counts. Here is a comparable instance from Azure. Version 3 brings 3 major improvements. First, we have updated our instances database. We now pull the latest instance types directly from AWS, GCP, Azure, and this is new, Akamai. Second, Akamai instances are now fully supported, giving you more options for your Kubernetes deployments. Third, and most exciting, the new cost sensitivity widget. Here's the problem we are solving. Your pod requests are estimates. What happens when reality doesn't match? The cost sensitivity widget shows you exactly that. Each band represents a 10% variance in your actual usage. Notice something important. When you use less than requested, you overpay. But when you use more, costs can spike dramatically because fewer pods fit per node. Let me show you another instance, a T2x large for the same workload. See how there is space for only 3 pods? There is a fair amount of space left, so if those pods were to use more resources on average, there is some extra buffer for them to grow. As you can see from the widget, the price doesn't change if the request increase of 10 or 20%, or if the request crosses the 20% and goes into 30, 40, and more. The price remains stable. I can't say the same for the other instance, which instead has growing costs as the requests increase. To explain the challenge, let's consider a typical application with requests and limits. In average, the actual memory and CPU consumption could be higher than the request, or it could be lower. When it's lower, you're still using all of your CPU and memory requests, since those are guaranteed to the process. So if you allocate a large amount of memory, but your app uses a fraction of it, the rest is wasted. No other process is allowed to use that memory or CPU. Over-allocating requests is a defensive strategy, but you end up paying for the resources that you don't use. In an ideal scenario, memory and CPU consumption are close to the actual value requested. In this particular case, you're paying, but not using. What if we under-allocate requests instead? When you define the request lower than the actual usage, your app uses more resources than what's guaranteed. If all apps are under-allocating requests, the node will be often overcommitted, and the kubelet will be forced to evict pods to maintain a reasonable amount of memory. In this case, you're overcommitting. Overcommitting could also trigger the autoscaler more frequently, leading to nodes being provisioned and destroyed. Let's have a look at an example. All the pods in these nodes are using more memory and CPU than the requests. The scheduler can find space to deploy an extra pod. When the pod is deployed, it uses more memory and CPU than what's been defined in the request. This will make the process cross the eviction threshold. The kubelet will be notified and will try to evict one of the existing pods. And now we're back at square one. The scheduler can see another space empty and it will try to deploy a pod. And the process will repeat itself. I want to thank Akamai who sponsored the changes for this version 3 of the calculator. You can find more links in the description.